Hello everyone, welcome back to Chapter 5 of Thermodynamics. I apologize if I cough or something because I've got the flu. But I'm still here making videos, do my best. No! Already a failure. That's okay, fix it later. Let's keep on moving on. So first off, we're talking about conservation of mass. Mass is the key word here. Because mass, like energy, can't be created or destroyed by a process. It's a conserved property. Now you can go back and forth, like this guy here tells you, but it's either always one or the other. Now, if we've got a closed system, that means the mass of the system is going to remain constant during the process. And why is that? Because it's a closed system, no mass is going in, no mass is going out, it's all just going to stay there. Now, a control volume is a very important detail we're going to be talking about quite a lot. Now, when I say control volume, what I'm simply saying is I might have a very complex system. It might have a series of pipes going through it. It might have water condensing on the pipes and dripping down. All these kinds of things can be happening all at once. I can even have water flowing through the pipes. Now, my control volume is simply how am I going to look at this very complex situation and make it into a more simple situation. So in this case, I'd probably say, you know what? This box right here is going to be my control volume. I have water flowing in, I have water flowing out. I have water flowing in, I have water flowing out. So this one is not a closed system, but either way. And I also maybe have steam going through here and condensing and falling down. By the way, everything I'm looking at is happening in here. And if the system is steady, then my mass is going to be steady as well. Now, another thing to think about is that mass is conserved even during chemical reactions. So like this whole E equals mc squared thing, you might think to yourself, well, when I go from hydrogen and oxygen to water, well, isn't that going to reduce the mass? Because there's energy released. But the amount of energy that's released by like a reaction like this is like 1 times 10 to the negative 10 kilograms worth. So it is infinitely small. It's not infinitely small, but very, very small. So no, this isn't really going to change things for us. Now, if you have nuclear reactions, that's different. We actually do have a significant portion of the mass that disappears. Okay, now another thing you might be thinking about is, well, if E equals mc squared, then what about kinetic energy? What about other types of energy, like potential energy? Does that increase my mass? Well, the interesting thing is potential energy, no, but kinetic energy, sort of. Technically, it's your inertia, but for all practical purposes, for us talking about it, we can say it's your mass. Now, if I have a 1,000 kilogram car right here, and it's going 20 meters per second, the mass would increase a little bit when it's moving. Now, how much is it? Picograms. It is a tiny amount of energy. Okay, let's keep on moving on. So the conservation of mass principle is simply saying, I have a total mass entering, a total mass leaving, and if there is a difference there, if more is entering than leaving, then the amount of mass I have in my system is going to go up. If more is leaving than entering, it's going to go down. So this guy right here will be positive or negative, depending on if more mass is going in or out of the system during your time frame. So let's look at this guy right here. We got a bathtub. We got 50 kilograms of water coming in during this particular time frame, delta T. We've got 30 kilograms going out. And so the amount of water that has to be in the bathtub is going to be 20 kilograms because conservation of mass. It doesn't go anywhere. It's not being like fused together. It's not being, we don't have a bunch of neutrons causing fission, hopefully. So with that, the total amount of mass is going to be remain constant. This right here is also equal to 50. Okay, so now that we have that, let's actually write it down in a bit fancier way. So we have these nice little equations here. They're very simple. Simply says the total amount of mass I have in the control volume will change. And it's based on how much mass I have at the end versus how much I have at the beginning. And an easier way to look at this a lot of times is as a rate. So this right here is the rate form. And that's simply saying that the amount of mass I have per time is going to be equal to the mass flowing in minus the mass flowing out. Okay. Now, these are our mass balance equations, and they're great for any control volume undergoing any kind of process. So it's really wonderful to use. My question then would be, how do I calculate the mass flow? Well, let's figure it out. So first off, let's look at our simple equation right here. Mass flowing in, mass flowing out, change in mass in the system. That's pretty simple. And this is going to get more complex, but I will simplify it at the end for you, just so you know. Now, one thing we need to realize is that we don't typically work with solids, we work with liquids or fluids at the very least. You don't have a machine that's running by heating up bricks and then using those bricks to then heat up another section. It's usually you're heating up water, you're heating up air, all kinds of other things. So if we're working with fluids, then we know that, okay, to calculate the mass flow of a fluid, I just have to know the density of the fluid times the volume of the fluid. So that's my mass right there. I can also integrate this and figure out how much mass I have based on density and volume. You don't have to use this all the time. Usually gets turned into a sum for doing things. Now, if that changes with time, then I have this. And this looks like our original part right here. So, okay, we're getting a connection here. We're seeing that if I know how the density and the volume element is changing with time, then I can figure out how my mass and my control volume is changing with time. Now, mass moves in and possibly out from somewhere, like right here. This is my control volume. Why do they make these random blobs? Because they like random blobs. And I have some little door here, dA, that mass is flowing out of. It's got a velocity v, and this is the normal vector. So we're simply saying that the velocity is not perfectly aligned to exit through that door. So putting it another way, if you're looking in our classroom, if we want to get a lot of people in our classroom or a lot of people out of our classroom all at once, then I need to have either a big door or fast people. So let's look at this again. So this is our next equation. It's simply saying the mass flowing out of one of these little doors, or in, is equal to the integral from my control surface, that is this edge right here, the whole surface, times the density. We're assuming a lot of times that our density is constant. This right here is the normal component of the velocity, because only the normal component really matters. And then we have our door dA right here. So dA is simply the size of our door. V dot n is the number of speed of the people. And with that, I get a better idea of how people are going in and out of my system. Or more likely, water, fluid, air, freon. Okay, now using this, we can turn our original equation, the one we had up here, and we can make a fancier version of it right here. This one you'll use a lot, but like I said, usually the integrals turn into sums. You'll have a nice little sized door. It'll be like, you'll have an area that you know. This won't be dA, then it'll just be A. You'll know the velocity, this will be V. And you'll have a few of these, so you'll just say, well, the sum of this. And so to give you that, I go ahead and write it down for you a little bit nicer. And if you're trying to figure out what this is right here, well, that is my velocity. Okay, let's keep going through. Okay, so we now have an idea of how to use our conservation mass equation. There's a lot of things we haven't talked about. For one, if you go into my aerodynamics course, or even fluids, you will learn that when air, water, whatever is flowing through a pipe, it doesn't have the same velocity everywhere. It's got a velocity that's much higher in the middle and very low at the edges, down to 0. And so if we're trying to deal with this, oh no, I've got to do an integral. I don't want to have to do an integral. That's going to be terrible. So what do? Well, typically instead of dealing with an integral of velocity or having some known velocity profile, I will just use an average velocity, which I can calculate in a very fancy way. However, most of the time this is just given to you in a problem statement. If you're solving for velocity, you're not solving for velocity distribution, you're solving for an average velocity. So with that, I can figure out a lot of different details. One, I can figure out what my volume flow rate is. That's only going to be equal to my average velocity times the area. And my mass flow rate is going to simply be my volume flow rate times the density. Okay. Okay. So now let's talk about steady flow processes. Now, as you know, not all of our flow processes are going to be steady. Some of them will have variations with time, but most often or not, we will have a steady flow process, which simply says that the mass flowing in and the mass flowing out is constant. Now, if the mass flowing in and the mass flowing out is constant, then the mass of my control volume does not change with time because it's already reached equilibrium. Boop, boop. So how do we work this out? So let's look at this particular guy right here. So what I have then is I have, okay, 2 kilograms per second going in here, 3 kilograms per second going in here, and then 5 kilograms per second going out here. So in this case, this is going to be steady flow. My control volume is going to be constant. There's no other outlets for it. And so it will have equal amounts flowing in and flowing out. Now this gives us a nice little equation here, both for inlets and exits. Now if we have a single stream, then we have just mass is going to be equal to mass out for a steady system, which in most cases means that the density is going to be constant. And so it'll simply be my velocity times my area at one point is equal to my velocity times my area at the other point. So V1A1 is equal to V2A2. That's not always the case. Your density can change, but sometimes it is. Okay, let's keep going a little bit further. Now, you might think about, okay, which one are we going to have more often? Honestly, a lot of the things we deal with are single stream. So this is like nozzles, diffusers, turbines, compressors. A lot of these things are single stream. There's one place that goes in, there's one place that goes out. And we're going to learn how to deal with all of those in this chapter, at least in a basic way. Spoiler alert, it's enthalpy. It's enthalpy all the time. And because I always jump ahead of myself, like I said, if the density is constant, then we have the volume flow rate in is equal to the volume flow rate out. Oh, there's an example. So this is where we're going to end it today, and I'll start this next time. Have a great day, everybody. Bye-bye.